Hello everyone, this is problem A. It is raining space dust. We are team 1095.
I'm Aqilla Keisachi Fatima.
I'm Eric Peter Leeb.
I'm Raisha Tabina Siregar.
Our coach is Mark Bowen and our institution is Waseda University. Cosmic dusts are tiny extraterrestrial particles, also called micrometeorites, that constantly fall through our atmosphere. They originate mainly from comets, asteroids, and interplanetary collisions. The dust contains various elements, and some of these might have been key ingredients for prebiotic chemistry, mainly carbon, nitrogen, phosphorus, and sulfur. We also know that the early Earth received up to 10,000 times more cosmic dust than today. During the last month, we've been trying to create a model that explains the changes different type of cosmic dust undergoes as it falls through the atmosphere. Specifically, we want to know the fraction of particles that fully ablate and melt during the process. The model should then be applied to different sizes and entry velocities and yield different results. Finally, we attempt to backtrack the process. In other words, given a certain distribution of dust on the Earth, calculate its possible sizes and entry velocities with which it would have fallen through the atmosphere. For our model, the following assumptions were made. Firstly, all dust particles considered are assumed to be spherical. All kinetic energy is converted into radiation and evaporates heat only. For simplicity, the entry angle is 0 degrees, although our model can calculate values for different angles too. We use the International Standard Atmospheric Model. Finally, we assume that the processes occur at the maximum temperatures the particle reaches while falling through the atmosphere.
Next, we're going to talk about the initial estimate to what happens to particles as they fall through Earth's atmosphere. So we're going to first derive the equation we used in MATLAB, in which we use it to compute the temperature of micrometeorite during atmospheric entry. This equation is the core of the heating pulse plots, and it balances the aerodynamic energy delivered to the particle with the energy lost by radiation and evaporation. So first, at the most basic level, we enforce an instantaneous energy balance, which you can see in equation 1. It is the power put into the particle by the atmosphere, which we call Pn, in which it has to equal to the power it lost. The two lost channels we include are radiation, which are thermal emission from the particle surface, as well as evaporation, the energy consumed to vaporize material. Next, what is Pn? It is physically the rate at which the kinetic energy of air molecules is deposited into the particle. It is a common aerodynamic estimate for that energy flux scales as density times v cubed, as you can see in equation number 2. So the first loss channel is thermal radiation. It is a hot sphere radiates from its surface area, and it follows the Stefan-Boltzmann law. And the second loss channel is evaporation or ablation. So if mass is lost at rate m, negative for mass loss, removing that material consumes energy equal to the latent heat times the mass flow. So for the final box equation here, we can see in equation 7, putting the three pieces together, it gives the operational equation we solve at each time step. And on the left is the aerodynamic heating, on the right is the two cooling terms. Because the evaporative rate depends on the temperature in a strong nonlinear way, this is an implicit equation for the temperature T. Next, we're going to move on to the next equation of Fv and Fm. Now that we've derived the temperature equation from energy balance, we also want to describe how much of the material is melted or vaporized as the temperature increases. To do this, we model the fraction of melted material Fm as a function of temperature using an Arrhenius type rate equation, as well as Fv. So this equation says that the rate of melting per degree of temperature depends on two things. First, the temperature-dependent reaction rate, which follows an Arrhenius exponential, and second, the amount of material still unmelted, represented by 1 minus Fm or 1 minus Fv. So what this equation tells us qualitatively is that at low temperature, e to the power of Ea over RT is very small, so dFm over dt is near zero, which means there's almost no melting occurring. As the temperature rises and the exponential term grows, dFm over dt increases sharply, and this is where the material rapidly melts or vaporizes. Finally, as Fm or Fv approaches 1, the 1 minus Fm or Fv factor drives the rate back down, so the process saturates it smoothly. So for assumptions, we calculated the Arrhenius constant A for two different cases, which are asteroids and comets. To find A, we made the assumption that 10% vaporize completely at a diameter of 50 micrometers, and this is an estimate consistent with the values given in supplementary figure 2 in the paper of Walton, Wrigley, Lipp et al. And finally, the activation energy for ablation of comets was derived from that of H2O, while that of asteroids was found from a mix of silicates and organics that are most abundant in C-type asteroids, which are the most common type of asteroids. So here are our calculated values, which are obtained from the maximum temperature we graphed through MATLAB. The left side is the one with constant velocity of 20 kilometers per second, and the right side is those of constant diameter of 50 micrometer per meter. For the results, here on the left side is the dependence of melted or vaporized fraction on the diameter, while the graph on the right shows the relationship between Fv with velocity, which will be essential for solving question 2. From the graphs, we can also tell that as v and d increases, Fv also increases. This relationship can be tracked back from our initial equation from the previous discussions. On the right graph, the velocity dependence becomes clearer because kinetic energy scales with v squared. Even small increases in entry speed produce large increases in heating. This is why the asteroidal curve rises sharply. Once it passes a critical velocity, the added energy rapidly accelerates melting and vaporization. Here we could see that the asteroidal particle have a much steeper exponential slope compared to the cometary ones. The difference comes from the material properties, in which asteroidal dust is denser and more heat resistant. So once its threshold is reached, ablation rises quickly. Cometary dust is more volatile and porous, so it begins ablation earlier but increases more slowly, in which it results in the flatter slope.
Now moving on to question 2, we are going to try to use our estimate to backtrack the distribution of cosmic particles that entered the Earth's atmosphere. So for initial assumptions, first of all, it was mentioned in the paper given that the nitrogen generally doesn't survive entering the atmosphere, while sulfur, carbon, and phosphorus generally survives falling through the atmosphere. And so we assume that F loss for nitrogen is 0.99 as which match the given value, and F loss for sulfur, carbon, and phosphorus we assume to be 0. And we also assume that all cosmic dust is made up of 20% comets and 80% asteroids based on the proportion of total accretion flux. And this value can actually be any values depending on the real condition. And next, the F sub m, the dust particles will become spherules as they enter the Earth's atmosphere, and so they will be distinct from the other non-melted particles when it reaches the Earth's surface. And also for the other constants, such as the chemical concentration beta and the flux value epsilon are known, and only F sub v is unknown. For derivation of gamma, so first of all, we're using here are our equations of gamma, which is the chemical concentration of each element in a given sediment. And this is derived from the given gamma equation 13, which was from the main paper. And here, beta sub E means the chemical composition of the Earth's chemicals, while beta sub X means the chemical composition of the chemicals that came from the dust particles. And here we differentiated the gamma for nitrogen as well as for sulfur, carbon, and phosphorus based on the survival rate of each and hence the F loss values that we assumed. Here we averaged the F sub V vaporization fraction value with constant diameter for comets and asteroids based on the proportion of total accretion flux, which is, as mentioned, 0.2 for cometary and 0.8 for asteroidal. And using the graph on the right side here, we can then interpolate the average velocity of both comets and asteroids for any given average F sub V. Now we are gonna do the conclusions and limitations of each problem.
As for problem 1, as we can see in the graph, asteroids ablate much quicker than comets according to our model. Besides the physical reasons, another reason might be the stark difference in the value of the Arrhenius constant A. The value is dependent on our initial condition of 10% ablation at 50 micrometers and 20 kilometers per second. Also, the activation energy might differ greatly for C-type comets, as it was derived from an average value of silicates and organics found in the asteroid.
Moving on for problem 2, first of all, we are able to backtrack the average velocity of asteroids and comets combined, given the diameter and chemical composition of cosmic dust which were found on Earth, although we cannot do it separately for asteroids and comets. And next, our sample model can also only run for the velocity values near the reference value, which was also used to solve the Arrhenius constant A, and we did this for simplicity. However, this can actually be used for any values of V, depending on what our initial reference value is. And lastly, the accuracy of the sample model, it can be estimated from the R-squared value from the graph itself. That's all from us. Thank you.